Hi students, in this class we are going to study the sag in the transmission lines. When you look at these conductors, they are not fully stretched, rather they are loosely hanging between the two transmission towers. If you stretch the conductors a little more, you can save the conductor material, but due to the excessive tension on the conductors, these conductors may break. In order to avoid that, these conductors are loosely hanging between the two towers. This vertical dip is called the sag in the transmission line. Now you consider the top conductor. This is the lowest point on the conductor. This is the point of support. This vertical distance between the point of support and the lowest point on the conductor is called sag in the transmission line. So the sag is defined as the difference in level between the point of support and the lowest point on the conductor. Now we have to derive an expression to find the sag in the transmission line. At first we consider the supports at equal levels. We consider this transmission line. The distance between the two supports is L meters. Let's consider a small portion of the conductor. We consider this portion OP. O is the lowest point on the conductor. Let it be the origin. So the coordinates are 0, 0. P has the coordinates x, y. So this distance is x and this vertical distance is y. When you consider this portion OP, two forces are acting on this conductor portion OP. One is the tension acting leftwards. Actually, this tension is due to the pull from the left side tower. The second force is due to its weight, which is acting downwards. As it is due to the weight, it is acting at the midpoint of the conductor portion OP. Weight of this portion OP is equal to weight per meter length into length of the conductor. Now, this is the length of the conductor. As the curvature is very small, this is approximately equal to the horizontal length, which is x. So this is weight per meter into the length of the conductor, which is approximately x. These two forces will cause two moments in this portion OP. Let me explain what is meant by moment of a force. Now this boy and his mom, they are pushing the door from the opposite sides with equal forces. So there is a state of equilibrium. If you want to experience the moment of a force, you need to consider one force at a time, or you need to lose the equilibrium. Now let's consider the force from the mom side alone. Suppose the boy suddenly jumps back. Now this door will rotate in this direction, or the door will swing in this direction. This is due to the force from the mom side. This is due to the moment of the force from the mom side. Now we consider the force from the boy side alone. Suppose the mom jumps back quickly. Now this door will swing in this direction. This is due to the moment of the force from the boy side. So the moment of a force causes the body to rotate in a particular direction. The magnitude of moment is equal to the force into the perpendicular distance. It's the distance between the point where the force is acting and the center of moments. Here the center of moments is same as the hinges of the door. The moment is equal to force into perpendicular distance. Now let's find out the moments due to these two forces T and Wx in the portion OP of the conductor. This OP is redrawn here. This is the center of moments here, about which the conductor will rotate. To find the moments, let's consider one force at a time. Let's consider the leftward force, the tension alone now. If there is no downward pull due to the gravity, then this conductor will rotate in this direction. Now the moment due to T is equal to the force into perpendicular distance. Here this is the perpendicular distance. This is equal to y, because here the coordinates are 0, 0. Here the coordinates are x, y. So the distance between the point where the force is acting and the center of moments, it is y. This is the moment due to the force T. Now let's consider the downward force alone. This is the position of the conductor. We'll consider this downward force alone, Wx alone. If there is no leftward pull, this conductor will rotate in this direction. Now the moment due to Wx, because this is Wx, the downward force is Wx into the distance between the point where the force is acting and the center of moments. This is x by 2, because this distance is x. So half of that distance is x by 2. This is equal to Wx square divided by 2. So these are the two moments acting on this portion OP of the conductor. If we equate these two moments, equating the moments, Ty is equal to Wx square divided by 2, or y is equal to Wx square divided by 2t. This is the general expression to find out the SAG. This is the expression of this curve. Y is equal to Wx square divided by 2t. So now if you want to find out this vertical distance y, you need to substitute this horizontal length x in this expression. If you want to find out this vertical length, substitute the corresponding horizontal length in this expression of the curve. Similarly, if you want to find out this vertical length, substitute this horizontal length x. And this vertical length is called a SAG. It is the distance between the point of support and the lowest point on the conductor. So here x is equal to L by 2. So y becomes W into L by 2 the whole square divided by 2t. This is equal to WL square divided by 8t. This is the expression to find the SAG when the supports are at equal level. When you look at the transmission conductors in the hilly areas, these conductors are suspended between the transmission towers at unequal levels. Now this bluish lines represents the transmission towers. They are at unequal levels. Now we consider this conductor. O is the lowest point on the conductor, which is the origin with the coordinates 0, 0. This distance between the origin and the left side tower is x1. The sag with respect to the left side tower is s1. The distance between the origin and the right side tower is x2. The sag with respect to the right side tower is s2. Now our general expression for this curve is y is equal to wx square divided by 2t. If we substitute x1 in this expression, we will get the sag s1. If we substitute x2 in this expression, we will get the sag s2. S1 can be written as w into x1 square by 2t. And S2 is equal to wx2 square divided by 2t. Let's find out S2 minus S1 is equal to w by 2t into x2 square minus x1 square. If you look at this picture, both sags are represented with respect to the common point O. So the difference between S2 and S1 is this height, which is equal to h. This is equal to h. S2 minus S1 is equal to h. Or w by 2t into, this is in the form of a square minus b square, which is equal to a minus b into a plus b. Here it is x2 minus x1 into x2 plus x1, which is equal to h. As you know, x1 plus x2 is equal to L, is the distance between the two towers. So x2 minus x1 is equal to 2th divided by w into L. Similarly, x2 plus x1 is the distance between the towers. This is equal to L. Now we got two expressions in terms of x2 and x1. Let's solve these two expressions. 1 plus 2 gives this minus x1 and the plus x1 getting cancelled. 2x2 is equal to L plus 2th divided by WL, or x2 is equal to L by 2 plus th divided by WL. Similarly, 2 minus 1 gives 2x1. This is equal to L minus 2th divided by WL, or x1 is equal to L by 2 minus th by WL. Now we got x1 and x2. So we can easily find out s1 is equal to w x1 square by 2t and s2 is equal to w x2 square divided by 2t. These are the expressions to find out the sag when the supports are at unequal levels. When you consider the transmission lines in the cold regions, these lines are coated with ice, and obviously the effect of wind will also be present. Now suppose this is the direction of wind blowing. This is the direction of wind. It is weight of the wind is W into WW. Now this is the ice coating, which is represented by the white color. The blue area represents the cross section of the conductor. The conductor has a diameter d ice coating has a radial thickness T. The weight of the conductor and the weight of ice both are acting downwards. So this is W plus W, weight of the conductor plus weight of ice coating. So these two are acting downwards. So we have two vectors. We need to find out the resultant vector now. Let's draw the parallelogram. The diagonal of this parallelogram will give the resultant vector. So this is the resultant vector. So this is Wt. So Wt is equal to root of W plus Wi the whole square plus Ww the whole square. So now we need to find out these three parameters separately. Weight of the conductor, weight of ice coating, weight due to the wind. W is the weight of the conductor per unit length, per 1 meter length, because we consider the conductor of 1 meter length. As you know, weight is equal to the density into density of the conductor material into volume. The volume is equal to, this is in the form of a cylinder. The conductor has a shape of the cylinder. That is pi r square h, which is the volume. Here it is pi into r is equal to d by 2. So it is pi d square by 4 into h is equal to 1. Because we consider 1 meter length conductor. So this is how we find out the volume of the conductor. So you will get the weight of the conductor using this expression. Now we need to find out the weight due to ice coating. Wi is the weight of ice loading per meter length. Which is equal to density of ice into volume of ice. Volume of ice per meter length. The volume of ice is equal to the whole volume minus volume of the conductor, which is equal to the whole volume is pi into d plus 2t the whole square by 4. The whole diameter is d plus t plus t. It is d plus 2t the whole square by 4 into the length of the conductor is 1 meter minus the weight of the conductor alone. It is pi d square by 4 into h. Again, h is equal to 1 meter. This is how we find out weight of the ice coating. Now let's find out Ww. Is the wind force per 1 meter length. This is equal to, as you know, force is equal to the pressure into area. It is wind pressure into the projected area of the conductor the projected area of the conductor per 1 meter length. So the projected area can be calculated as projected area is equal to, so the wind is blowing from the side of the conductor. When the wind is blowing in this direction, the wind sees the conductor like a rectangular piece. Here the height is equal to d plus 2t and this length is equal to 1 meter because we consider the conductor of 1 meter length. So the area of this rectangular piece is equal to d plus 2t into 1. So the projected area is equal to d plus 2t. This is the height or the width into the length is 1 meter. So once we find out these three values W, Wi and Ww, you can easily find out the sag as sag is equal to Wt into L square divided by 8t. Actually this sag is a slanting sag in the direction of Wt. If you want to find out the vertical sag is equal to this S into cos theta. From this triangle we can find out the cos theta. So this is the expression to find out the sag considering the effect of wind and ice loading.